let's go ahead and get started. My name is Rhonda Grimm. I work for PerfTech, and we make the island router. So we are going to be covering basically how networks work. It's a very ground floor webinar, just to kind of connect some dots with terms you've heard, get a basic understanding about how data moves around networks and around the internet. And so, yeah, let's start with, there's always been a loose analogy that computer networks are a lot like the postal system. Both are trying to send things around this huge network in the most efficient way possible. So looking at that analogy, let's just say Alice has a birthday card for her college friend, Bob. And Alice lives in the UK and Bob lives in New York. And if you're a letter, you want the best path possible. So Alice, writes out the card. She puts it in a mailbox in Bath, England. The post guy comes up. He takes it to the post office nearby. And then the card goes by train to London, and then it goes on to, by air to New York. And oh my gosh, it arrives at New York City post office. Mail carrier comes in, delivers the card to Bob's office building, and Bob gets the card. So that's kind of how the whole process works. Everybody along the step, they have their direction. They're like, I know I need to get it to, the next stop, but the post guy in the UK has no idea how to get it to the building, but it doesn't matter. They all take and they do their little hop. Well, it's the same kind of thing with computers. So instead of taking a physical birthday card, computers send things in packets. Packets are just ones and zeros, and it's just this sequence of numbers, and everything is done in packets. Every web page you request, every picture you send your buddy, every email, it's all packets. So going back to our little analogy, every envelope, every card has an address. So you've got the sender's address and you've got the destination address. So in a packet, same kind of thing. It's you've got the envelope, if you will, called the header, has the address of the sender and the destination. And then the payload is the birthday card or whatever you're sending. So it's like, that's great. So now what? How do you get the data where it's going? So it's this great idea called packet switching. And it's a mode where you break things into little bitty bits, send them independently, and each bit gets, on its way, the most optimum route, and then gets reassembled at its destination. So you buy the birthday card for Bob, then you cut it up into a bunch of little bitty pieces. You put each little piece in an envelope with Bob's address as the destinations. You're the origin. And then each of those little envelopes goes all the way in the most efficient route possible. And they are taken and reassembled in order at their destination. So each step along the way, has limited knowledge. It knows that it needs to get it to the next place that's closest and fastest. So that's cool. So let's just say you want to send this picture. It's a 1 megabyte picture, and you want to send it to your buddy in Japan. There's 8 bits in a byte, so there's 8 million bits in this picture. So what could possibly go wrong? The likelihood something's going to get corrupted. So if you tried to send it in all one chunk, you're gonna lose some information, and then you'd have to start all over again. So that's no good. So instead, cut it up into little bitty pieces. And the biggest Ethernet packet is basically 1,500 bytes. So as it's reassembling at the other end, it says, hey, I'm missing, packet number, blah, blah, blah. Then all you need to do is it goes back, it requests that back, and it'll retransmit just that one small part. So it makes it really efficient. So it's not only it's one of those things in the past, and I remember these days, you had, you wanted to send something to another office, let's just say in France. You would have to establish a dedicated line. You'd call up the phone company, you get a dedicated line, and you'd be able to send data across this thing. But when it wasn't being used, it just sat there, and they were so expensive. So with packet switching, you're able to get things on their way, but through this humongous pipe, the internet, and the pipe can be shared, and all the packets they just need their address to where they're going and some protocols to push them on the way, and then they get to where they need to be. So it's the genius of this whole internet model. We go into the whole TCP/IP layer stack in networking 201, but it really is a pretty cool model, and you go into depth about how it all works. But that's basically how things move around the internet. So what we'll start right now then is, what does that look like in the stuff you guys do every day? How does that affect the home network? So let's talk to Alice again. Alice lives at 614 Spring Drive. She's got a bunch of IoT devices. She's got, her laptop and her mesh, and what isn't wireless plugs into the switch, which plugs into the router. Then she's got this cool home automation system that has, her smart fridge and all her smart thermostats, and she's got this big controller, and the controller is hardwired into the switch, which goes into the router. And then you've got this rockin' home theater system, and you got the media controller and all these things that plug into the switch, which plug into the router. So the router, this whole thing goes in to the router, out to the modem, out to the internet. So you can see everything rides on the router. And that's kind of where our focus is going to be today. Like, what role does the router play? So as we talked about, computers communicate in packets. Packets need addresses. So there's two types of addresses. Every computer or device on the internet has two of them. They got an IP address and they've got a MAC ID. So in order to get to its destination, you need both. The router uses both the IP address and the MAC address to send to a particular device on the LAN. We'll talk more about MAC IDs and other modules, but for our purposes right now, we're going to focus on the IP address. So going back to Alice's cool home automation system, this is how she sees her network. She's got the theater, she's got the devices. This is how Alice's router sees the network. It's all numbers. And you'll notice behind the modem there, they all have this similar structure, the 192.168.2, and then some unique number at the end. And you'll run into those all the time with the routers you install, the 192.168. There's other common configurations. But let's look real quick at the IP address structure. And we're going to talk right now about IPv4. You'll have heard of IPv6, I'm sure, but for now, let's talk about this. IPv4 address is composed of 4 sets of 3 decimal numbers. And one part is the network address, and one part's the host address. And it can be different. You get into subnet masks and stuff, and that tells you which part of those 4 octets are, the 4 sets are the network address and which is the host. But for our purposes, in this case, and what you'll run into the most, the network address is typically the first 3 sets, and the host address is typically the last set. So every network has a unique network address, and every device on the network has a unique host address. So that's what you'll typically see. So going back to our envelope, The network address, the 192.168.2, that's kind of like the street address. And the last 3 digits, like your laptop, remember they all have unique numbers, every device. So maybe your laptop ends in 122 and your cell phone ends in 102. That's kind of like the suite number. It's a way to just divide it a little bit more. And when you look at it, you can think of it in terms also of the network address is like a street, like Spruce Street. But the host address, those last 3 digits, those are like the house number. And just to belabor this point, so maybe you're at Cedia and you order pizza. The pizza guy can get to the hotel, which is like the 192.168.2, but without room numbers, he has no idea where to deliver the pizza. So the room number in this example would be, of course, the host address. So, you know, you've heard of IPv4, which is what we're talking about with those 4 sets of 3 decimal numbers. There's IPv6, which is like 8 sets of 4 hexadecimal digits. It's incredibly big. But we'll talk in terms of IPv4, but why the IPv6? Why introduce this kind of complexity? Well, it turns out when this whole internet thing got going, we're like, oh, this is awesome. We've got 4 sets of 3 decimal numbers. That's 4.3 billion possible addresses. This is great. Well, I'm sitting there at my desk and I'm looking at 6 devices. And so it doesn't take long before you start like, we're going to run out of addresses. So sure enough, there was quite the push. So now with IPv6 and all those sets of 4, you can get 340 undecillion, no idea. But, you know, we're not going to run out of IP addresses. So that's the genesis of the IPv4, IPv6. But it also introduces this concept of public versus private addresses. So public addresses are reachable from anywhere on the internet, and private addresses are hidden. So they're not reachable on the internet. So that 192.168.2. So why public and private? Well, turns out it all kind of goes back to, there's some security aspects, but a lot of it was we're running out of addresses on the IPv4. So if you look at the left side of the screen, reachable from the internet, your ISP gives you a modem, and that modem has a public IP address on the WAN port there. So in this case, 203.10.113.12. You can get to this this router from anywhere on the internet, but behind it, the router says, no. I've got 400 devices behind my router because I have a huge house with, you know, a bunch of people, and I don't want to use all those addresses. So I'm going to get a private IP address, the 192.168.2, and then I'm going to give every individual device a unique number. Now, it's all hidden. It's not reachable from the internet. Everything is behind this firewall, if you will, and these are just private addresses, and the router takes care of that. So public address on the one side, and then private address with all the devices on the other. So it begs the question, if you've got private IP addresses and you're wanting somebody to connect to you from the internet, how in the world do they find you? So enter network address translation. NAT was developed to conserve IP addresses. And so what it does, it also helps protect your privacy because you're not reachable behind your NAT router. So in a way, private addresses are a lot like sending an envelope with an anonymous originator. You can't really expect a response if they don't know how to write back to you. So if you look at, again, with the network, all the devices are behind this private IP, And then there's the public facing 203.10.113.12. So the way NAT works, you're wanting to send something out, it takes your private IP address, translates it to a public IP address, sends the request out to the internet, gets the response, translates it back to the requesting device. So, and all home and SMB routers are NAT routers. So let's take Alice. She is at 192.168.2 and her laptop is a host address of 10. So the router translates that private IP to a public facing 203.10.113.12, sends the request to YouTube. YouTube says, sure, let me give you my page back. The router then translates that back to Alice's device. So she gets her YouTube page. So then you have to say, well, where do those private addresses come from anyway? Well, here comes the DHCP server. It stands for Dynamic Host Configuration Protocol, but nonetheless, every client on a network, every device has a DHCP client in it, and the router has a DHCP server. And, they connect to the switch. So every device needs an IP address, and it's the DHCP server's job to assign IP addresses to the host devices. If you figure that the way that it does it, one thing you'll know is that because of the dynamic host, the addresses are assigned dynamically. So what does that all mean? So here's basically the process. Let's just say that's Alice's laptop. Says, hey, DHCP server, I need an IP address. And the DHCP server says, well, how would you like 192.168.2.30? The device says, I would love that one. Thank you. I'll take it. So then it says, okay, the DHCP server says, you can have it until Tuesday at 5 p.m. But let me know if you need it longer than that. So halfway through this lease period, it's going to query, you're still cool with the 192.168.30. And it'll go on like that. So it basically gives your entire network a pool of addresses to use. You can specify it in the DHCP scope. You can say, okay, I need a certain number of addresses. And that way, if the lease time, if you keep needing it, that's great. But otherwise, if the device is offline or unplugged or it's just never used, or you had a guest come in and they never came back, you can throw that thing at the end of the lease period back into the pool. Then you're not wasting a bunch of addresses. So DHCP is awesome because it's easy, it's automatic, and it's scalable for as many devices as you need. But some things need a specific set address. Like, for example, the controllers you install. Those, it's really nice, or like the media players, media centers, they really need a very reliable, dependable address so that the other devices can find them easily. So one option is to use DHCP reservations. And those are good because it basically says, controller, you will always have the same address. It is like a reservation, and no matter what, I will always have .34. And that way, all the devices who need it can rely on it and not have to worry. So the alternative to DHCP, you've probably heard this before, is static IP addresses. And they're still used, but as the name implies, they don't change. And it used to be the way all IP addresses were assigned, which would have been a personal disaster for me. It didn't really take long to realize this is not easy. So you would have to configure and track each device. You'd have to manually assign it by the user and network administrator. You had to make sure there were no duplicates. And in the network change, you had to manually change all those IP addresses. So, What could possibly go wrong? So even though you still have uses for static IP addresses, most network installers today use DHCP reservations due to the issues. So let's do a quick review on what we've learned so far in 20 minutes. Every device has a unique address. The address can be either public or private. The NAT translates the private address to a public IP so people can find us. And the DHCP server just doles out all these IP addresses from a pool. And some addresses need to be fixed. So you have DHCP reservations or static IP address so that you're able to have a reliable address for that. So how does all this work if Alice wants to go to YouTube? Well, one other thing we talked about, a little hinted at before, is the protocols. The protocols are the things that push things around the network. They're basically a set of rules that everything follows, so things aren't just crashing into each other. So NAT and DHCP are just two of the protocols used within the local area network. HTTPS, SMTP, DNS, things that you'll hear are protocols you'll see on the internet. So let's go back to Alice going to YouTube. What is all involved in doing that? Well, it's a website, so it has a bunch of web pages in it, and those web pages are written in HTML, and those pages use HTTP and HTTPS. The S stands for the secure. That's what you see in your address bar when you're typing in a website. And those are the protocols for sending and receiving that kind of information. So Alice wants to go to YouTube. Her computer sends a request using HTTPS to youtube.com. YouTube receives the request, responds, sends her the web page. But how does YouTube find her computer? So here we go, and vice versa, basically. Enter the domain name system. You've heard of DNS, and it's web host names versus IP addresses. Again, computers think in terms of numbers. Humans think in terms of names. So names don't change. It's always youtube.com. But IP addresses can change for a variety of reasons. And plus, who wants to memorize a bunch of IP addresses for their favorite sites? So it's kind of like in the old days when you had a phone book and you knew your friend's name. You didn't necessarily remember their phone number or their address for that matter, but there was a way to look it all up. Same thing with DNS. It's basically the phone book for the internet. So it turns names, domain names, into IP addresses and allows you to get where you want to go. So, for example, when you want to go to YouTube, you type it into your browser. The router makes a DNS query to see which unique IP address is associated with YouTube. The first thing it'll do is it'll look locally. Your computer will look locally in the browser cache, like Firefox, to see if you've been there before. And a lot of times you have, and it'll grab it. But if it's not there, you need the phone book. So the DNS server resolves that what IP address does youtube.com belong to. So basically, it's just this humongous database. It's the biggest database in the world, I believe. And it makes all these requests through a series of DNS servers located everywhere. It does it in fractions of a second. And it really is quite impressive. So now the circle's complete. Alice wants to go to YouTube. Using NAT, the router converts Alice's private IP address assigned by the DHCP server to the router's public IP address. It then does a DNS lookup on youtube.com and sends a request over to YouTube, which has this humongous IPv6 address. YouTube receives it and wants to send it back to the public address it has for Alice's network. So it goes back over HTTPS. The router receives the YouTube page from its IP address. and translates it from its public to its public IP address. And then using NAT, the router translates that public IP to the private network address, finds Alice's host address, and sends it to the private IP address that belongs to Alice, and a web page arrives. So congratulations, that is how things move around the network and around the internet. I will throw in a couple of more ideas that we don't really get into here as much. We save these for 201, but you'll hear a couple of terms. You'll hear VPNs and you'll hear VLANs. So VPNs, what we're talking about when we are talking about VPNs, we're not talking about, I want to go watch the soccer game in Brazil, so I'm gonna get one of those services and do that thing. This is what we're talking about is like, I want to connect my vacation home to my main home. I want to connect from, office to home, maybe multiple offices together, maybe a bunch of Subway, stores, or an employee or a parent back at the office wanting to connect back to home while traveling. So basically, VPNs create a secure digital private pipe, just a tunnel. They share two secrets. They share a secret on this end and a secret on this end, private and public keys. And once that private connection has been established through encryption, you can just send data all day long. It's hidden and it's very, very secure. So it's basically, one of our colleagues used to say, it's like taking a long, long Ethernet cable from your office and plugging it into your home router. But anyway, that's the VPN. And then there's this notion about VLANs, virtual local area networks. And it's basically a collection of devices that you allow to talk to each other. They don't even have to be necessarily, in the same place. Maybe you want to put all your guests who come to your home or office into a guest network so that they don't have access to your normal resources. So you can put them into a VLAN. You might have a printer that has the check paper in it, and you may only want people who work in accounting to have access to that printer. So you would create a VLAN for those guys. Security cameras, you might have on their own VLAN, keep them out of the way, Alexas, that sort of thing. So those are a couple of terms that we can go into further in the next course, but just they do seem to pop up quite a bit. So networking components, one of the things, kind of the nuts and bolts of networks, you'll, you got your devices, you've got your Wi-Fi, access points or your mesh, you've got some cabling, you got a switch, you got a router, you got a modem, and then you got the path out to the internet. So let's look at some of these LANs, series of devices linked to form a network. Wi-Fi uses radio waves to connect all the wireless devices together. Cabling connects the wired stuff to the switch. Switch forwards data between the devices on the same network. Routers forward data between networks, including the internet. Your ISP gives you a modem and gives you internet service. And then, of course, the internet is this humongous network that connects other computers and networks all over the world. So these are some of the components. So let's look at some of just drill down onto some of them. Ethernet cabling, it's what people use. There's all kinds of different cabling. You've heard of coax. It's usually used for the modem, although that's changing rapidly. You've got fiber optic cable. You've got unshielded twisted pair. You've got patch panel cables. So it's almost always preferable to hardwire something with Ethernet cabling as opposed to just throwing it on Wi-Fi. The connections tend to be more stable over Ethernet and faster. So a few things you want to pay attention to with regard to cabling is length of cable, the shielding it uses, the data rate, and where it will be installed. So cable lengths are a big deal. Ethernet cables are designed to work over a maximum distance of 328 feet. Using single pieces cable longer than that will reduce performance. So bottom line, don't be out of spec on your Ethernet cable. And here's just a quick chart. The gray zone is sort of the cabling that you'll run into, the Cat5, the Cat5e, and the Cat6 category is what that stands for. Back in the day, Cat1, I mean, that was telephone and modem lines. And we know one thing that's interesting to me, you go back to Cat3, it's like 10 megabits per second. And it just started escalating so quickly. And you'll see the usage is, you know, Cat6 you'll find in big homes, commercial buildings, the stuff we see a lot, Cat5e, residential homes. So these are some of the specs. Some of the speeds they can accommodate, the maximum distance, but it is hard to believe that not that long ago from Cat 2 and 3 all the way up to Cat 8, 25 gigabits per second, my goodness. So that is cabling. You'll hear about PoE, power over an Ethernet cabling. It's super helpful. It's typically will save you time and cost just because electricians aren't required. You reduce the number of outlets. Basically, the cable gets the power from the Ethernet is able to transport through the device itself, and it derives its power from the device. So you don't have to sit there and look for plugs. Reduces energy cost. It's flexible. You're not tethered to a certain part of the room that has the outlet. It's safe because it's not high voltage. It's very, very reliable, and it's quite scalable. So that's just another type of cabling you'll run into PoE. Then we've got switches. A switch connects multiple devices to create a network, basically. And there's two types of switches: unmanaged, sorry about the dogs barking in the background, unmanaged switches and managed switches. So the way they differ basically in capability, security, and cost and complexity. As you can imagine, unmanaged switches, they're kind of like a basic hub. You can plug everything into it. It doesn't have a whole lot of added features, usually no security capabilities, and they're very inexpensive. Managed switches, you can configure ports to talk to specific ports. They have all kinds of security settings in them. And as you can imagine, they are quite expensive. It can be quite expensive. Wi-Fi. Wi-Fi is just a standard. It's a family of network protocols. The 802.11, you'll run into that quite a bit. It's commonly used in local area networking and allows devices to exchange data via radio waves. You'll see that you'll hear that Wi-Fi 7 is on the horizon. Wi-Fi 6 we're running into quite a bit, and it's great because it just gets faster and faster. Wi-Fi 6 is touting Wi-Fi 7 speeds. The protocol complete standards for Wi-Fi 7 have yet to be ratified, but they're coming quickly. It's considered 2.4 times faster, can reach up to 5 gigabits per second. It has great channel bandwidth. It effectively doubles the Wi-Fi speed. So it's kind of like going from a 2-lane road to a 4-lane road. And then the data density within that roadway is like 20% theoretically higher. So, it's like a 3-dimensional, like going through the pipe. So it's cool. And it's gonna likely put a little bit more load on the router. So that's something we'll talk about. So on Wi-Fi, you've got APs, access points, and then you've got mesh systems. And so when you're wiring up a house, especially a large multi-floor house, you'll likely need multiple access points or a mesh. Access points are great. Each individual access point is hardwired into the switch. And then you can project the Wi-Fi signal around to every room or area of the house you need. So it's very efficient and typically preserves the speeds. A mesh network, you only really have to plug one node into the switch, and then the other broadcasts to the other nodes. It's very, very convenient, and it's easy to link then multiple access points together, multiple nodes together. But you know, the pros on the mesh systems, they're easier to install, they're more flexible, but performance tends to suffer a little bit because your non-wired nodes are going over the air, and you're going to lose some performance. So modems and the internet service speeds. So ISP provides a couple of different functions. When you order service, they're either going to give you a standalone modem, in which case you'll need a separate router and access points or mesh, or they're going to give you one of these things called a modem router Wi-Fi combo. We call it an all-in-one internally, but it has everything you need. It has the router, and it has the modem and the Wi-Fi access. Trouble is, they're rarely, if ever, enterprise grade, and they're just often not up to date in terms of technology, and often refurbished and not necessarily up to the demands of the networks today. But the other thing you get from your ISP is your customers sign up for a data plan, and you know, the speeds these days, they're typically pretty good. 100 megabits per second is good for multiple users and devices. Anything, the 500 megabits per second to a gigabit per second, do basically anything on multiple devices at high speed. And the faster the connection, the more you typically pay. But just because you have this big honking connection, you know, doesn't mean you're necessarily going to get multi-gig speeds on your network. And again, let's focus on the router. How can it be? Well, some routers are a lot more efficient than others. So why is a Porsche, you know, engine faster than the Chevy big block when the Chevy engine is twice as big? Porsche engine is just much more efficient. You take an engine rated at 500 horsepower, but by the time it gets through all the resistance and the axle and transmission to the wheels, I mean, you're not necessarily getting those speeds. Same thing with a router. In networks, lots of routers advertise these multi-gig speeds. It's kind of like the quarter pounder. It's a quarter pounder, but before you cook it, by the time you add in the VPNs, the VLANs, the logging, the filtering, the security, your multi-gig router can now put out less than a gigabit per second. So inexpensive, non-enterprise grade routers just don't have the efficiency to keep up. So that's kind of where we lead to with the point of this whole thing. Like, where are we going with all this knowledge? And to me, it kind of comes down to your network rides on the router. So you got to choose wisely. Home networks today are like what small business networks were in 2018, let's say. There's so much to home networks now. There's climate, there's appliances, there's, you know, smart this, smart that, voice assistants, IoT. So home networks are coming under great amounts of load. So long gone are the days, I had one of these, you know, when you could just get a kind of cheap wireless router and everything was great. But even the high-end routers are problematic. On paper, you know, they check a lot of boxes. They tout those high port speeds, but then they bog down as soon as you turn up the features. And sometimes updates need hand-holding. And sometimes you have to do it in the middle of the night so as not to disrupt the whole network, especially like work from home situations. They often need to be rebooted, and there's subscription fees, and everything is typically built on open source code, which creates lots of security risks. And they're complex. Networks in general, they're just hard. So the more you have to touch that network or go back or configure the network, there goes, you know, profit margins. So one of the things our company, we make a router called Islands, and we have a background, 40 years. We were at the beginning of networking. The guy who's 2 doors down from me actually invented the first commercial LAN protocol, ArcNet. We created the first LAN to internet connectivity box back in the 90s, and we were purchased by Nortel Networks for that, and went on to become the best-selling VPN router. And then we spent the last 20 years in the carrier space. And let me tell you, carriers are unforgiving. So you have to be fast, you have to be efficient. You cannot take down the network for any reason to upgrade or anything like that. So very, very stringent demands. So what we did back in 2019, when we started thinking, man, it'd be great to have a router for all of us to use in our homes, but that really held up. So we took all that expertise, 40 years of expertise, all that carrier grade, just the demands that the carriers put on the different equipment in their core. We put that all into Islands. So we can tout 2 million packets per second. You remember all those packets we learned about? They go screaming through the wire. With all features enabled, not just the raw throughput before you turn on anything. It's 2 million packets per second, period. It's wired by design to get the maximum effectiveness for the speeds. It's able to handle 130,000 connections per second. So what does that mean? Well, you know, web pages like weather.com that are so complex, they have ads and they've got all this stuff that's coming in from a whole bunch of different servers. All that, those connections, you got to be fast. And that's why some of these web pages take so long to load. But we are able to accommodate that at 130,000 connection per second. Most routers don't even publish these numbers. We are built on our own code. We've been using it for decades, and it's the same code we developed in the carrier networks. So it's not open source. And I mein, this one unit supports 5,000 devices. It supports more, but we just stopped counting. A lot of competitors only have the ability to support 100, 150 devices before you start running into trouble. So there's no worries with scalability. And it's easy. You don't need a PhD to install it. And just to give a nod to the architecture, Island, we use very high-end hardware. It's a quad-core 64-bit. If you pop open an Arachnus, I think this was the 310. It's a dual-core 880, 32-bit processor. We have 4 gig of error-correcting memory. No one puts error-correcting memory in these types of routers. We have 4 gig of error-correcting memory. They had half a gig of single-channel 16-bit. We have 64 gigabytes of flash storage. They've got 64 megabytes. And, you know, we have an internal power supplies. We don't like power bricks. Everything's created and manufactured in the US. And we have battery to retain the time while powered off. So it's just it's these kind of touches that put us in a different class of product. One of the things too is we wanted something to be easy. We have a reputation for making hard things easy, hard technologies. When you first wanted to connect your business to the internet, it used to be a really big hassle. It was you had to load, you know, protocol stacks, everything on each individual computer. It was a mess. So we were able to do that and automate that and make it just truly plug and play. So traditional router interfaces, they're exhausting. There are rules and they think in terms of IP addresses. We think in terms of devices, users, and groups. We bake everything you need into the router. It's pre-configured, it's automatic. You can change it if you want, but we took best practices and pre-configured everything. Seamless updates, you don't necessarily have to take the network down. Instant VPN setup, that's a really cool, you can connect to islands together in literally 10 seconds. And then we have a thing called Smart Swap router replacement, where it'll go in and learn the existing network, bring in over all the existing IP addresses, all the existing configuration, and then it makes router replacement extremely easy. So, and on top of that, just all the features you'd expect in an enterprise grade router. So with that, that is all I had, and it gives us some time for questions in the chat if anybody has any. Lee, if you would like to talk a little bit more about Smart Swap.
Sure. What Smart Swap is designed to do is make it a little easier to exchange an existing router of some other brand for an island router, in an existing deployment. It's not needed for new deployments, but it's very useful when you're trying to replace an existing router and minimize the disruption to the network. What Smart Swap does is it attempts to learn the IP addresses of all of the existing devices on a network. So let's say you have a customer that's got brand X router, and you want to replace that with an island. So what you do is, and there's instructions on the website as well as in the app for how to do this. And it is important that you follow those steps in the proper order. It'll make this as painless as possible. But basically, you plug the island, any port on an island, into your existing LAN. So for example, if you have an Ethernet switch in your network, just take a port on your existing Ethernet switch and plug it into the island. Just as an aside, if you have multiple VLANs, you want to make sure that's a trunked port for those of you who know about VLANs and care to use them. But at any rate, you plug it into your existing network and power up the island. It will learn the IP addresses of all of the existing devices on the network. It will learn where the existing router is, what its IP address is, and so on and so forth. Learns all that stuff in just a few seconds. It doesn't take long at all. Once that's learned, then what you do at that point is unplug the existing router from the network and then plug a different port on the island into your modem, your cable modem or your fiber termination or what have you. The island will detect that the old router has gone away and that the island is now plugged into the WAN, and it will essentially assume the identity of the old router. In other words, it'll change its IP address on the LAN to match that of the old router, and it will maintain in its DHCP server, it'll maintain all the existing addresses that devices had before they switch to the island. So it means you don't have to go into the island manually before you hook it to the customer's network and program the proper IP addresses and all of that. It learns that from the existing network. There are some limitations. For example, it can't learn things like port forwards and DHCP reservations from the existing router. So after you've switched to the island, all you have to do at that point is go into the app. We make it very easy to establish those. For example, DHCP reservations. If you have devices that have DHCP reservations, you can go into each of those devices on the island, hit the button that says DHCP reservation. It will have already filled in the current IP address of the device. So at that point, all you basically have to do is click save. So it doesn't do everything, but it certainly makes things easier because it learns all those existing device addresses and so on. So very, very useful. It really is a time saver for replacing an existing router with an island.
Okay, well, let's see. I think can give you 7 minutes of your day back, and we will make this recording available to Dave. And thank you so much for your time. Really appreciate it.